Hello everyone. In today's lecture, we are going to discuss about synchronous up counters. In the previous sections, we have discussed about flip-flops. So flip-flops are the basic building block of counters. So now synchronous up counter is a device which can count any particular event on the basis of how many times the particular event has occurred. Counters are implemented using flip-flops. In a synchronous counter, clock input across all the flip-flops uses the same source. And the clock is evenly distributed to all the flip-flops. The different applications, are you confused why the synchronous up counters are being used? It is used in machine motion control in the case of electrical application, motor RPM, counter for measuring RPMs, rotatory shaft encoders, then digital clocks, digital watches, alarm systems. All these uses up counters. Wherever we need to count, everywhere, even PC incrementer, program counter incrementation, everywhere up counters plays its major role. Now we are going to design an up counter. For designing an up counter, we need to follow certain steps. First is we have to decide on the number of flip-flops and also the type of flip-flop which we are going to use. Draw the excitation table for the flip-flop which we have chosen. Then draw the state diagram followed by the excitation table for the logic diagram. Draw K-map to find the minimal Boolean expression. Draw the logical diagram for the up counter finally. Now we are going to see on a problem statement, that is to design a synchronous 3-bit up counter. So first we are going to follow step 1, that is it states how many number of flip-flops and what type of flip-flop. We are asked to design a 3-bit up counter. So if we want to design a 3-bit counter, then we need 3 flip-flops. If it is 4-bit, 4 flip-flop, 5-bit, 5 flip-flop, and so on. And now we are going to consider JK flip-flop for our purpose. Any flip-flop, D or T or any flip-flop can be used. So step 2 is to draw the excitation table of JK flip-flop. So this is the which we have derived in the previous classes from the working principle. For different sets of input, truth table was framed, then characteristic table was framed. From the characteristic table, excitation table was derived. Please refer the previous videos. So this is the excitation table. Now we have to draw the state diagram. State diagram shows the number of states. Now see, it's a 3-bit counter. So if it is 3 bits, it can count 2 power 3 values. That is 8 values starting from 0 to 7, right? So here it is 0, right? 0, 1, 2, 3, 4, 5, 6 and 7. Totally 8 states are there. These individual rounds are known as states. These are different states, right? So this is known as state diagram. Since it is an up counter, after 0, 1 will be counted. After 1, 2, 2 after 2. That is why the arrows are being in this direction. And it can count only totally 8 values if it is a 3-bit counter. And so after 7, it resets again back to 0. Yes, so this present state and the next state is shown by a state diagram. After the state diagram, using the present and next states, we'll be drawing the excitation table for the logical diagram. So this is the present state and the next state. If you see here, if the present state is 0, 0 and 0, the next state will be 1. In this state, if the present state is 0, 0, 0, next state will be 1. If the present state is 0, 0, 1, next state will be 0, 1, 0. So if the present state is 0, 0, 1, next state will be 0, 1, 0. Likewise, from the state table, we will be writing the present states and the next states. All these are binary values of the present states and the next state. Then, let us consider this QC. So for QC, consider this present state and the next state, that is QC and QC plus 1. So for QC and QC plus 1, it is 0 and 0. If the present state and next state is 0 and 0, what will be the value of J and K? It is 0 and don't care, right? So see, JC and KC will be 0 and don't care. Similarly, coming to QB. QB is present state, which is 0. QB plus 1, the present state is 0. If it is 0, 0, from the excitation table of JK flip-flop, if it is 0, 0, J will be 0 and K will be don't care. So if you see here, J will be B, that is QB and QB plus 1, so will be 0 and K don't care. Similarly, the same is applicable to other two, right? So likewise, with the present state and the next state, we will be writing the values of J and K with the help of the excitation table. Once after framing this excitation table, we have to draw the K map for all the outputs. Here the outputs are the inputs of the flip-flops. Our task is to draw the logic diagram. For that, we need to find the inputs. We know the outputs, that is counter. It has to count from 0 to 7 since it is a 3-bit counter. We need to give the inputs appropriately, and so we have to find the value of J and K for all the three flip-flops. So it's the task here. So A, B and C are the three flip-flops which has two inputs each, JAKA, JBKB and JCKC, right? So altogether 6 values we have to find. Obviously, from the truth table we can use a K-map to find. And see the K-map, from the K-map, after grouping, we'll be arriving at these Boolean expressions. We'll be arriving at these Boolean expressions. And from the Boolean expression, we'll be drawing the logical diagram. If you see here, this is a flip-flop. These are the 3 flip-flops which we require. The 3 flip-flops, and this is the input. If you see here, this is the first flip-flop. For the first flip-flop, J and K are 1, so logical 1 is given. For the second flip-flop, see J is QA, so for Q, see QA is being given to J. Similarly, QA goes for KB is also QA, so for KB also the QA comes here. Then similarly for JC and KC, the values are QA, QB. So we'll be taking QA from here, QB from here. Using an AND gate, we'll find QA, QB, and that is being given to JC and KC. This is how the inputs are given to all the flip-flops. And with this input, we will get the counted value here, QA, QB, and QC. This is free assessment, and thank you.